Hello to you all, class of 2014 matriculants. This is your time. My name is AB Abram, and we're all up and ready to give you a most jam-packed educational show ever. This is Learn Extra Live, and we're here to bang it with Tracy.
Hi, Abram. How are you?
I'm fine, thanks, and you?
Good, thanks. I'm excited to get going and get started with our guinea pigs here. Because they got the new curriculum, so it's going to be
must be
interesting.
exciting, hey? Because
It's exciting and scary, but you know what? I think it's going to be a great year, and I'm excited for them, and they can do this.
but with the right skills and resources that we have as mindset, you can't go wrong.
Practice, practice, practice.
You can't,
No.
exactly. What are we doing today?
Today we're going to do momentum and impulse. Hopefully most of them have done it already. I really am hoping that. I know my learners have actually just written their first test on it. So
Ooh,
they
wow.
don't like me very much right now, but it's okay. So I just have to quickly do this. Hello to my learners. Byron, hello.
Can you hear them shouting?
Yeah, I can hear
Hi.
it. And if he isn't watching, I'm going to smack him at school tomorrow. Just that, didn't say that. I will reprimand him quite severely.
All right.
Yes.
Minus
so
some marks there.
no, but we're doing momentum and impulse. It's a really nice section. It's actually a nice, easy section to get marks if you get the concept. So hopefully we can get those foundations.
Flow
today.
together, exactly. Well, to help you, here are some resources that we have for you. We have notes that you can download all for free. Visit our website, which is learn.mindset.co.za. Follow us on Twitter at LearnExtra. Like our page and invite all your friends to like our page also on Facebook. Currently, we're sitting at about 65,000 and more likes on Facebook. So let's get everybody join in the Mindset Tribe. But for today, we also have a challenge question.
We do, which I'm going to do in a second once I've introduced the lesson, but I've got a challenge question for them, so we're going to see how they do.
Well, we'll post it on Facebook and make sure that your answers are on that post. Yeah, let's
Good.
do this.
Should we get going?
Yeah.
Okay, brilliant. Guys, please interact with us. We really want to answer your questions, okay? We want to see what you guys are doing. So just in terms of what are we doing today, we are going to discuss the important terms in momentum and impulse. It's really important. Hopefully you'll get the difference between some of them. And then we're going to discuss impulse, conservation of momentum, and conservation of kinetic energy, which is a really important part of this section. Okay? But straight away, let's just jump in there and give you the challenge question. And it's a very important question because it comes up a lot. Wrong way. There we go. So this is our challenge question, all right? It is going to be posted on Facebook. I think it's on its way, but let's just read it together. When a large truck collides with a car, often the car will experience a greater amount of damage. This is because, and now you need to choose the correct answer. Number A, the car experiences a greater force than the truck. Okay, that's the first one. B, the truck experiences a smaller impulse. Okay. C, the car experiences a greater acceleration. Or D, the truck's change, say in momentum is smaller, not as momentum. Okay, that should be is. The truck's change in momentum is smaller. So I'm asking you, why do cars get more damage when they collide with a truck? Okay, is it because the car experiences a greater force? Because the truck experiences a smaller impulse? Because the car has a greater acceleration, or because the truck's change in momentum is smaller. Okay, so you need to have a think about it, and these answers have been very specifically set up because we'll see how you do it to show some misconceptions, and hopefully we'll help you out along the way. Okay, so have a think about it. Hopefully by the end of the show you'll have the right answer, and we'll have a lot of people with the right answer. That's what we want, okay? And then they can just start putting their answers on, hey?
Exactly.
C, A, C, B. Don't need to put an explanation, okay? But let's...
Well, you can, just to show us how much you understand.
That would be
the
great.
concept,
I'd
yeah.
actually really like to hear some of those explanations, especially if you don't get it right. That sounds bad. But this is what I say to my learners all the time. You have to try in order for your teacher to help you. When I have a learner who says, I didn't do my homework because I didn't understand, I actually can't help them understand because I need to see what you've done wrong to see what's going on in your head.
Exactly. Try and fail rather than failing to try.
Absolutely. I like that. I like that. Okay. So let's go through some of the theory, just quick, and this should all be hopefully a bit of revision, okay? So the first thing is momentum is a vector. So we've got to remind ourselves what that means. With momentum being a vector, whoops, let me not put text. I want the pen. That's what I was looking for, okay? Vector means momentum has to have both direction and magnitude, size, okay? So that's really important. So whenever you do a momentum question, and they just say calculate momentum, change momentum, anything like that, make sure you've got to put a direction in. Big, big problem if you don't. Number 2, it's defined, this is the definition, as the product of velocity and mass, which gives me P equals mv. Momentum's probably one of the few physical quantities that gets used almost correctly in everyday language. Because we often talk about momentum, and we say in a rugby match, and we'll say that the momentum of the rugby player when he got tackled is what put him over the try line. Okay, and what commentators are referring to is the motion. Okay, and they're talking about how fast he was going, or how big he is, or something to that effect. So, and that's almost correct. So it's okay if we think of momentum in terms of motion. Objects have to be moving to get motion. Okay, so that's quite important. Now the equation is P equals mv, and remember it's a little p, not capital. Capital P stands for power, and they will mark you wrong. Okay, so P is momentum, m is mass, v is velocity. Remember, you have to do it in SI units, so mass is in kilograms, velocity in meters per second, and together those units give me the units of momentum. Because if I go, this is kilogram, meters per second. Kilogram meters per second, straight from the units of mass and velocity. Okay, so that's really nice. Must have a direction. Now, added to that, I don't think you're going to get a lot of questions with a single object bouncing off a wall, all of that sort of stuff, but we're going to deal with those just now. That brings us to the whole concept of impulse. Now, impulse is a strange little physical quantity because impulse is probably the only physical quantity you deal with that doesn't have its own symbol, which makes it so difficult sometimes to conceptualize, okay? Impulse, and I'm just going to write this in here, impulse is, come pen, is F net delta t, okay? Impulse is defined, I'm going to come back to the change momentum in a second, as the product of the net force and the time the force is experienced. Together, force times time gives me impulse. But the nice thing about impulse is it's equal to an object's change in momentum. So it's equal to delta p. We need to now just quickly discuss how we can change this equation for delta p. Now, delta p means that I take final momentum minus initial, okay, which means I take my object's final velocity over here. Now watch what I'm doing. The mass of the object stays constant. We have to assume that, okay? We're not concerned about the fact that when a crash happens with a car, the side mirror falls off and the hubcap falls off and the mass, we just assume everything stays the same. So mass is a constant. I can take out the m, which gives me vf minus vi, and final minus initial gives me change in velocity. So impulse is mass times change in velocity. You are going to use this concept over and over and over again, because in a collision, okay, if we can make this time much bigger, okay, in a collision, we make the force experienced much smaller, because the change in momentum is going to be the same. So for example, in cricket, when you catch a cricket ball, okay, now as a girl, I've done this many times growing up, I've since learnt my lesson, not very well, but that's why I don't play these games. What do girls do? Sorry ladies, if you do play cricket, you probably don't, so just bear with me, and maybe some boys, is you put out your hands and you see the cricket ball coming. First of all, you close your eyes, which is a bad thing, but you put it out your hands and you do this, and you hope for the best, and then the ball hits you and you scream because it hurts, okay, because it's fast. But why is it fast? Because you try and stop the ball really quickly, so it's a big force. But if you did like the cricketers do, and you went and you tried to pull your hands back with the ball, and you actually pull it into yourself so you don't lose it, okay, is as you catch the ball and you come down with it, you're taking a longer time to stop it, so the force gets smaller. It's still going from what if, say, it was going 20 meters per second to 0, it's just taking a longer time. If it takes a longer time, then your net force gets smaller, and that's what we want. Okay, so it works all the time. That's why cars are designed to crumple. Okay, on the backs and the sides and airbags and all of those sort of things. The fact that they do that is to reduce the amount of time, to increase the amount of time it takes to stop, to decrease force, okay? Impulse is a vector, which means impulse has direction, okay? Next important thing about impulse is its units. Impulse is measured in Newton seconds, taken again from force and time. Please be careful. It is equal in magnitude and direction to change in momentum, but has different units. So when you say work out change in momentum in one part of the question, and then they say to you, what's the impulse? Remember to change the units. Okay, very important. Then we get to the law of conservation of momentum. This is a great law because this all says to us that the total linear momentum in a closed system remains constant in both magnitude and direction. So when two objects come together and they hit together, like two cars or two billiard balls, snooker balls, okay, or two tennis balls or two dogs or two toy trains, whatever the case may be, if it's a closed system means no friction, no air resistance, no external forces. In a car crash, it means that you haven't slammed on brakes in the process. The momentum is conserved. So whatever the total momentum was of the 2 or 3 or 4 objects, as the case may be, was before they collided, that's what the total will be afterwards, no matter what happens, whether they stick together, whether they fall apart, however the case may be, as well as in an explosion. Okay, we often just say a collision, but we can also mean an explosion being something like shooting a cannonball out of a cannon or firing a bullet out of a gun. It's quite a violent part of your curriculum, which is a bit sad. Or, which is the question I did with my learners today, you can have two toy trains, for example, and there's a compressed spring between them that then breaks and it allows them to move apart. Okay, that's an explosion. But it means that your initial, sum of your initial, that's what sigma means, okay, it's from maths. Sigma means total, okay, so that little sign there means total or sum of. Total initial momentum is equal to your total final momentum, and that equation can change depending on the situation. And let me just clarify what I mean by that is if you, so we've written down total, okay, so we have, and we can also write before, we don't have to write initial, so we go before, and make sure your sigma sign looks like a sigma sign. That should say after, not initial, sorry. Okay, so this is after, make sure it looks like a sigma sign. If you have two objects that are separate, come together, collide, move apart, then we would say, well, we have my two objects which have an initial velocity. So I would add both of their initial momentums, that's what those two are. And afterwards, I would add their finals, okay? So this is one way that this equation can look. If the two objects come together and they collide and they stick together, like in a car crash, for example, okay, often the cars get tangled up. Afterwards, they're no longer two objects, so what happens is my equation changes. So they started off as two things, but they've ended up as one. So we would add their masses together and realize they both have the same final velocity. With the gun, they start off as the same object, so you would write them, you would add their masses together first, you have an initial velocity, and then afterwards there's an explosion, so you get two separate objects, okay? All three of these situations tells me that we have total momentum before, the sum of all my initial momentums is equal to the sum of the momentums afterwards. Okay? So you can break it up in all different ways, but the science, the principle, is this line over here. That's the principle, and then you break it down depending on the situation. And don't forget direction, direction, direction. Because you're often going to have objects that can be moving in the same direction, they can be moving in opposite directions, that one could be stationary, one could be moving. You must choose a sign convention. Very, very important. And then lastly, kinetic energy. When the kinetic energy of a system is conserved, it's an elastic collision. What does that mean? That means when I add the total kinetic energy of both my objects before they collide, and I add the total kinetic energy after they collide, and it's the same amount, kinetic energy is conserved, and it's elastic. Extremely, extremely, extremely rare in everyday situations, because that kinetic energy that they have gets changed and it gets transferred. It's not disappearing, it's not lost. Please be careful. Your conservation of energy law still stands. Okay, you cannot make or create or destroy energy, but you can change it. So the kinetic energy now changes into sound and into heat, and because of friction, because they knock together. Sometimes light, but that's quite rare, okay? But kinetic energy is not conserved during an inelastic collision. So your total kinetic energy before is different to the energy after. Doesn't have to be less. In an explosion, your kinetic energy afterwards is definitely more. An explosion can never be elastic. Ever, ever, ever. Not a chance. Okay, just remember, just quickly, before we go to a break, because I think we're overloading with information right now. Come now. Is kinetic energy equals a half mv squared. Okay, you've done that equation lots and lots and lots since grade 10. All right, so hopefully that's starting to give you some insight into the challenge question as you're thinking about it. But I think maybe it's time for a break, and then we'll get into some nitty-gritty questions.
Yes, but the mindsetters have work to do during the break.
Absolutely.
We have some test yourself questions that are on the notes. There's like 5 of them. So make sure that you get on them during this time. And we'll see some answers later on. But otherwise, keep your questions also coming on facebook.com/learnextra. See you after the break. Welcome back, Matrix. Now, a wise man once said that procrastination stops positive momentum. So never procrastinate. I hope you have done those test yourself questions.
I hope so too, though I'm not sure they would have had enough time to do all of them in the break.
But they're very quick and easy, I think. Okay, it'll be a homework.
Yeah.
Whilst you're at home, you have a homework.
Yeah, some of them you got to work out. I chose them deliberately. Don't.
Right. So do them perfectly. Take your time and concentrate.
There we go. You know what the nice thing is here, guys, is I'm looking at, and I know most of you go multiple choice, you know, it's like monkey puzzle, that's what they call them, or multiple guess, as the case may be. But don't do that. I'm actually going to show you, hopefully we'll get there, is how to work them out. Some of them are easy. It'll take you like 10 seconds because you know theory. Some of them you've actually got to work some stuff out. So
concentrate.
Listen to him.
I like that. Okay, well, let's improve our skills now.
Let's move on, and I'm hoping questions are coming. So what we have here is a really nice question. It's from the Exemplar 2008, paper 1. Okay, and it says, collisions happen on the roads in our country daily, and with all the rain we've had in Gauteng lately, it's actually been quite bad. Let's just be honest, because people, it's amazing how it rains and people can't drive. And in fact, momentum, friction, all of those things all come into account now. This is your science at work.
And I think also environmental issue like affects us a lot. So they contribute to our science also.
Oh,
so
no,
it's geography and science.
There we go. It's all integrated. I love it. Okay.
And maths.
Now, and maths, yeah. We don't do maths and science. Anyway, in one of these collisions, a car of mass 1,600 kilograms. So we've got a car of mass 1,600 traveling at a speed of 30 meters per second to the left. So we've got a direction, okay, collides head-on with a minibus of mass 3,000. I'm going to change it using a different color because now I'm dealing with a different object, traveling at 20 meters per second to the right. The two vehicles then move together as a unit. So my third important thing here is that they move together. So they become one object at the end. So they start off, and it's nice, they gave you a diagram. They start off apart, they collide, and afterwards they're one object, okay? Now, grade 12s, everything I've done here, where I've underlined stuff in color and that sort of thing, that's what I would do when writing a test. Or when I do the memos to tests or exams that I set, I actually sit with the paper and do all of this sort of thing, because it's important to visualize it. And a lot of times there's so much information you actually can't sort it out in your head without highlighting stuff, okay? Now, the first thing they say, calculate the velocity of the two vehicles after the collision. The nice thing is, in this question, is they gave you a diagram. If they don't, draw a diagram with boxes for the minibus and the car. Okay, draw the same thing. That's what I do. I can't draw to save my life, grade 12s. If I had to stop teaching, I would not become an artist, because I would never get paid. I would be homeless within a week, okay? So we know we can't do that. So I would draw it with boxes and afterwards. And in fact, I don't even draw the collision. I just draw a double line. My learners laugh at me lots. Anyway, next thing you have to do is you need to choose a direction as positive. That is your choice, okay? Everyone has a preference, and I'm going to choose, just because I always do it, is I'm going to actually choose to the right as positive. And I'm going to write it down, okay? I'm choosing to the right as positive. Now, what that means is that the car's initial velocity becomes negative, and I write it into the diagram. This is where you're going to make your mistake with the minus 30, because you're going to forget. So please be careful here. Okay? Now we want and this is our minibus, so I'm going to call this M, and this is my car, I'm going to call it C. You can leave them as 1 and 2, but by calling it the minibus and by calling it the car, we know exactly what we're talking about. So we want the velocity after the collision. As soon as we see the word collision, we know it's a moment conservation question. So we go, fine. That means I've got to start with the fact that total momentum before. So I'm going to put it as before. Okay, equals my total momentum after. Okay, there were 2 objects before the collision, so I'm going to write it down as 2 objects before. I'm calling it, that's the car, that's fine. And then we've got the minibus. Okay. And then afterwards, they become one object. Okay, let me just make that look like a little M, because at the moment it just looks terrible. All right. So jeez. Okay, the brain has gone on strike, just so you know. Can't blame the board this time. Okay, and we want their final velocity. So we go back to our diagram. I'm just going to go up a little bit so we can see it. The car has a mass of 1,600, and it's going at minus 30. Okay, don't forget the minus. The minibus has a mass of 3,000, and it's going at 20. Afterwards, they collide. They become one object. So I'm going to add the car to the minibus. And now we want VF, okay? At this point, if your algebra and your multiplication skills are really, really good, and you know how to use your calculator really, really well, you can go straight to the final answer. You really can. But we're not going to do that, because I know sometimes we make stupid mistakes, so we're going to do every step. So the first thing we're going to have to do, okay, is let's go over here, and let's go this side. It doesn't actually really matter. We're going to start with the 16. Okay, I know what I need. Sorry, I just want to take this off, because I don't want the smart ink. There we go. Okay, so, wow. There we go. Let's start again. All right. So we're going to go 1,600 times 30, and it's going to be minus 30. That gives me 48,000. That's actually minus 48,000. Okay. Then to that, we're going to add the 3,000 times 20. I don't want that. Times 20. And that gives me 60,000. Okay. And 3,000 plus 1,600 is 4,600. Okay. And so now we're going to have, so from here, I'm going to take the 60,000, I'm going to minus the 48. And so we get 12,000. Okay, so over here, I've got 12,000. And that's equal to 4,600 times VF. So VF, and now we're going to divide that by the 4,600. And remember, not as a fraction, so we get 2,61. Be careful with the rounding off, 2,61. I got a positive answer, and we said that to the right is positive, which means it's 2,61 meters per second to the right, which actually does make logical sense because the minibus was bigger than the car, and there wasn't that much of a difference between, oh man, there we go. There wasn't that much of a difference between their velocities, but there was a much bigger difference between their masses, okay? Now, do the necessary calculations to show that the collision was inelastic. In other words, show that energy is not conserved. What does that mean? We actually have to do two calculations. We're going to add together the kinetic energy before, okay, and then we're going to do a second calculation and add the kinetic energy after. Okay, so before the collision, there were two separate objects. So we're going to take the minibus and the minibus's initial velocity, and I'm just going to quickly get rid of this. Oh, got a nice squeaky board. And we're going to do this. And I know you can't hear the squeaking, but I can. And it's not in my head before you say something. Okay? So, anyway, moving on. Okay, so we know the minibus's mass, okay, which is 3,000. We know that its initial velocity was 20. We know the car had a mass of 1,600, and it had an initial velocity of minus 30. The direction doesn't change. Guys, I'm just going to actually go to the final answer from here because I think you can manage the maths because it's more the concept. And what we're going to get is we get 1,320,000 joules. Okay, so that's before the collision. Afterwards, okay, so now we're going to do the after part. That's hideous. Okay, so afterwards, now watch what I do with the equation, okay? So it's a half, and remember that their masses got added to, their masses got added together. Okay, don't use them as separate ones. So that gives me a half. We have 3,000 plus 1,600. Oh man, let's just do this quickly, go away. And its final velocity, we worked down to 2,61 squared. And now we get, okay, let me just find my answer. Now watch here, 15,667,83 joules. Look at the difference. This is huge, okay? Huge, huge difference. Think about, I'm pretty sure you've seen a car crash on TV. Hopefully you've never been in one, but you've seen one live, and they are noisy, okay? Noisy, noisy, noisy. Lots of sound. It's where the kinetic energy is going. Also, it's the energy, there's heat produced, lots and lots and lots of friction. Okay, so that's where the energy is going. Now, the question was to show that the collision was inelastic. So we're not quite finished yet. So now we can say, therefore, the collision is inelastic, okay? Why? Because, and you write this out, okay, because your total kinetic energy before is not equal to the kinetic energy after. Okay, very important. Now they add another thing. Same question. The billboard below advertises a car from a certain manufacturer, okay? And it's got safety first, both in one package. They've got an airbag, they've got a crumple zone, and they say to you, use your knowledge of momentum and impulse to justify how the safety features mentioned in the advertisement contribute to the safety of passengers. The crumple zone and the airbag increase, okay, so the two safety features increase changing time, okay, the stopping time. And I'm going to put this in point form. So it increases the stopping time. Now, the change in momentum of both of the car remains constant in any collision, okay? It remains constant. Whether it takes 10 seconds to stop, 1 second to stop, if it was going at 120 kilometers per hour and it gets to 0, it's the same change in momentum, okay? Obviously, the longer it takes to stop, the better, which means that impulse, let's just put this up here, is constant. Why? Because F net delta t is equal to my change in momentum. So, if delta t increases, then F net decreases. The smaller F net is, the less damage you experience. Okay? The smaller F net is, the less damage you experience. These questions come up all the time. All the time. So, so important. Okay. Let's do one more. Quick. We're going to show you how to get there. A man of mass 87 kilograms. Okay, so we've got a man of mass 87 kilograms. He's on roller skates, moving horizontally at a constant speed in a straight line. Yay. Sees a boy of mass 22 kilograms standing directly in his path. This is not good. The man grabs the boy, and that shouldn't be there. And they continue in a straight line at 2.4 meters per second. Now they say calculate the man's speed. That means I don't need direction. Just before he grabs the boy. Ignore the effects of friction. There's no diagram here. Okay, so now I'm going to show you what I mean by the way I draw these diagrams. So what does it say? We have a man. Now we know I can't draw, so just go with me. So we have a man. Okay. On a roller skate. Okay. He's 87 kilograms. We don't know what his initial velocity is. He's moving in this direction. He sees a boy, so it's a little one, in his way. He then grabs the boy, so we stay on this, and now we have the man and the boy on the same skateboard, and now they're going at 2.4 meters per second. I think it's safe to assume that the boy and the man on the skateboard are going in the same direction that the man was going in when we started. Okay, I don't really see that they're going to go backwards, but you never know. But I don't think they will. They also said to me that the boy was 22 kilograms, so we're going to add that in. We're going to ignore all effects of friction. Yay, we like this. This is a collision. That means we need to use conservation of momentum. So here we go. We're going to start off by saying that we're going to use total momentum before equals my total momentum afterwards. Okay. Before there were two objects. We have the man and his initial velocity, and we have the boy and his initial velocity. Afterwards, they're one object. So we have the man and the boy and their final velocity. Now we go right. The man was 87 kilograms. We don't know his initial velocity. The boy is 22. The boy is stationary when the man grabs him, so the boy's initial velocity is 0. Very important. And afterwards, they become one object. Okay, and what we end up with here is that your final velocity, we're going to quickly work it out, actually, because I've got a feeling that my answer in my notes is wrong. No, it's not. Okay, we don't need to do this. Sorry, I'm just getting myself confused. It's always important. Yeah. Anyway, so that means here we're going to have 87 and his initial velocity. And final velocity is why I got confused myself, because I didn't actually write in here that that I know what this final velocity is, because I do know it. It's 2,4. Okay, I should have written it in, and that gives me 261,6. So the man's initial velocity is 3,01 meters per second. Okay, he slows down because we get a bigger mass. Now they ask you, is the collision elastic? You have to answer the question. Use a calculation to support your answer. What does that mean? That means you've got to do, you cannot do this and go EK before equals EK after and then work it out. This is a proof, like in maths. So we're going to go, we look at EK before, okay, which means we're looking at the man plus the boy's kinetic energy. And hopefully somebody is screaming at the TV right now, the boy's kinetic energy is 0. I know. So we take in here, the man was 86. Ooh, wow. That was a nice scribble. Let's not go back to primary school. 87, we just worked out that this is 3,01. And you can actually just put 0 there straight away, because we know it's 0, and we get 394,11. Afterwards, they are one thing. So we add the mass of the man and the mass of the boy. So we have a half times 87 plus 22, and they said, and that should be a squared, 2,4 squared, and that gives us 313,92. And no, the collision is not elastic, because kinetic energy before is not equal to kinetic energy after. See how small those energies are, though, compared to the car? Absolutely, smaller momentum. Okay, wow.
Wow, you've got too much energy.
Well, you know, it's still early days. It's only February, so, you know, it's important.
It's important.
Anyway, yes.
It's a great start otherwise for the matriculants. But otherwise, Mindsetters, I just want to wish you all the best to everybody that is writing their subs. I have the timetable, and it's posted on our Facebook page. There's a link for the timetable. If you know your friend or somebody that you know, or you are supplementing this year, all the best, because, you know, as Mindset, we believe in you, and we will always be here for you. See you after the break. Welcome back, Mindsetters. I'm seeing a lot of answers on the challenge question, but now we're about to get the right answer. Tracy, you up and ready for this?
Okay, guys, let's do this. Now, with the challenge question, when I put it together for you guys, I thought about it because it came up in a final exam as a long question, something very similar to this, and I wanted to try and address some very important misconceptions, okay? So, a truck collides with a car, and the car experiences a greater amount of damage, which we know from everyday experience that's exactly what happens, okay? The very first thing that gets said to us is that the car experiences a greater force, or the inverse of that is you say, well, the truck experiences a smaller force, because the car is smaller, and the truck is bigger, so the truck must hit the car bigger. This goes against Newton's third law, which you learnt last year. Remember, Newton's third law says that if body A exerts a force on body B, then body B exerts exactly the same force on body A just in the opposite direction. So the same happens with a car and a truck. Okay, the car and the truck exerts exactly the same force on each other. So this is not true. The car does not experience a greater force at all. It can't, okay? Then they say, well, then the truck must experience a smaller impulse. Because when we look at it, we go, well, impulse, which has got something to do with force, is F net delta T. So to experience a smaller impulse, sometimes we go, well, maybe the car takes less time to stop. And the truck, because it's so big, which is what happens, takes a longer time to stop, experiences a smaller force, smaller impulse. Well, that doesn't make any sense, because remember that the truck and the car experience the same force. So they pretty much, when we do our calculations and we say, well, the truck and the car hit together, we don't ever go that the truck can experience the force for a shorter time than the car, because the truck and the car must, for them to experience a force on each other, must be in contact for the same amount of time. This is a contact force. So it can't be, because it's a smaller impulse, okay? So we've already ruled out A and we've ruled out B. Then we go, hang on, wait. C says the car experiences a greater acceleration. And right now, some of you are going, where did acceleration come from? Because nowhere in this have I spoken about acceleration. Now watch what I'm going to do, because C is actually the answer. If I go F net delta T, remember it's equal to M delta V, okay? The truck and the car both will come to a stop. The truck and the car experience the same force for the same amount of time, because they have to be in contact, which means both the truck and the car experience the same change in momentum, which straight away tells me D can't be the answer, because they have the same change in momentum. Okay? Now, by process of elimination, C has to be the answer, but now I want to explain to you why. When we look at this, okay, and we say, well, if I look at just the force, F net would be equal to M delta V divided by delta T, which is actually Newton's second law in terms of momentum. Newton's second law says that the net force on an object is equal to the rate of change in momentum. So they experience the same net force, okay, same time. Now let's look here. Delta V over delta T is acceleration. Acceleration is change in velocity over change in time. Time stays the same. A car has a smaller mass, which means it must have a bigger change in velocity in order to stop, or to have the same change in momentum, okay? There must be a bigger change in momentum and change in velocity. And often there is, because the car will probably change direction, which gives us a big change in velocity, okay? If there's a big change in velocity, then there's a greater acceleration. And when it comes to how damaged the car becomes, it's dependent on the amount of acceleration it experiences. So the greater the acceleration, in other words, the greater the change in velocity, the more damage it experiences. Remember, with the truck, there's a bigger mass, so it has a smaller change in velocity to get to the same change in momentum. All right, so the answer to the challenge question was C. Did we get lots of C's?
Yeah, we
did.
did.
We?
Yeah.
Yay! Well done. And I'm hoping that it wasn't just a guess, but that there was a process of elimination and you'd worked it through the same way I did. Okay, so well done, guys. That's brilliant. Good start. All right, let's do some questions.
From the mindset.
Let's jump in there and see if I can help them.
Let's start with Vincent.
Vincent,
yeah,
okay?
Da Vinci. Vincent
Yes.
River says, what if I find that after collision, the kinetic energy after you subtract the kinetic energy before it gives me a negative difference? So would the collision be inelastic?
Okay, I really like this question, okay, because what, Vincent, I'm assuming what your teacher has told you to do is to say, well, if I'm looking at kinetic energy, and I say, well, if I look at the change in kinetic energy, and I take the final, and I minus it from the initial, and I end up with a negative value, okay? So in other words, my final answer there becomes negative. So my final is less than my initial. Absolutely, it's inelastic, okay? As soon as, when you take it this way around and you don't get 0 here, it's absolutely inelastic because there's a difference. Now, where this will happen is in something like an explosion. So, for example, when a gun lets off a bullet, okay, before the collision happens, the kinetic energy is actually, or the explosion is actually 0, because the gun and the bullet aren't moving and they're one object. After the explosion, okay, you're going to get it's the other way around. He's getting a final that's smaller, no, initial that's smaller than, bigger than, I got it. Okay, final that's small. Should I shut up now? Let's try this again. Your final is going to be different to your initial. This isn't what he was asking me. Okay. If you get negative, absolutely. So in other words, you've got a small number minus a big number. Your kinetic gets smaller. Absolutely inelastic. That's not an explosion. That's a normal collision. Because it gets smaller because what happens is you lose kinetic energy to sound, to friction, that sort of thing. You can get a situation, this is what I'm trying to tell you, where your final is bigger than the initial. That's where I was trying to go with that. Then you would end up with a positive value over here, because that's with a gun with an explosion, because now we're turning potential energy into kinetic energy. Okay, so Vincent, absolutely, if you get a negative answer, or you get any answer, be it negative or positive with a change in kinetic energy between the beginning and the end, it is inelastic. Because either you've lost, and I use that loosely, but you've transferred kinetic energy into sound or heat or light or something like that, or you've gained, I also use it loosely, you've changed potential energy or chemical energy or compressed spring energy into kinetic. So absolutely that's inelastic. Okay.
Here's another question following
Yes.
to that one. It's
Yes.
from Zamangwe Nyazintle.
Yeah.
Why do we use kinetic energy to prove if the collision is elastic or inelastic?
Because when we're talking about whether it's elastic or inelastic, we're looking at the energy changes, okay? And we've got to do something that can be conserved, and we can't always deal with it in terms of mechanical energy, because mechanical is just potential or kinetic, which you've done before, but we do know that energy is always conserved, okay? We know that. Energy can never be created or destroyed, it's simply transferred. In a collision situation, though, we have lots of forms of energy. So scientists needed to define elastic and inelastic in terms of an energy that was the easiest one to look at, and kinetics to do with motion. Remember, the whole thing with momentum is motion. So we wanted to use moving energy, okay, which is why we only look at kinetic. Plus, we haven't taught you how to measure sound energy or friction, heat energy due to friction and stuff. So we'd never add that in straight away. Okay, yeah.
Cool. Moving
Yes.
right along. Here's another one from Bright.
Yes.
Is it invalid to use kg.m for
Okay,
over
so
s for impulse?
what they're using, kg
Dot m
oh,
over s
okay.
for impulse.
Yes, it is. It's so similar. It's one of those things where we've got to remember what we're being asked. Okay, this unit is momentum, P. Okay, when I'm talking about impulse, I'm talking about the change in momentum, which is why I have to use Newton seconds, NS, okay? So whenever I talk about impulse, impulse is F net delta T. The unit must be Newton seconds, okay? Because that's the change in momentum, not just momentum. So kilogram meters per second, that's just momentum, or change in momentum, has to be Newton seconds for impulse, absolutely. Yeah.
Awesome. Then we can take last one for now.
Yeah, so we can.
All right, here's one from Linda Guth. I think also other mindsetters are having a bit of a trouble with that question. What is the difference between change in momentum and conservation of momentum?
There we go. Okay, guys, change in momentum simply means we look at an object. It could be a single object, it could be more than one object, but something happens with the momentum. So, for example, and in fact, this was one of the questions in the test yourself, where we have a tennis ball that hits a wall and bounces back. The motion of the object changes. The velocity changes. So when I look at change in momentum, I'm looking at a single object, so I only use one mass, and I'm looking at how its velocity changes, essentially. Okay, that's change in momentum. And when an object's momentum changes, it has impulse, it experiences an impulse. When I look at conservation of momentum, I'm now talking about two objects that collide, that now interact with each other, and as a result, their velocities change. Okay, so when I set up the equation, and we would put total momentum before, but I would now have two masses. Okay, I'm now looking at two separate objects that do something and their momentum changes. Okay, so conservation of momentum is the collision or the explosion. We're looking at the interaction between two objects. Okay, change in momentum is simply the interaction of one object against a wall, on a floor, bouncing, throwing it up and down. That's change in momentum. Okay, conservation, collision or explosion. Change in momentum, single object that's changing its velocity for some reason.
Cool. Mpoza?
Yes.
Mpoza says, is Newton per second the same as kilogram per second?
No, there's Newton per second doesn't exist. I'm assuming, did she write it? Did she write Newton per second?
Newton.
Okay.
Yeah.
Newton per second, ns to the minus 1 would be force divided by time. I don't even think that exists. And kilogram per second is mass divided by time. That doesn't exist either. So, no. I'm not actually sure what you were trying to ask me, Sweet Pea.
Okay, well,
I think you're just getting a bit confused with the mass along the way. Yeah,
not the same.
Yeah.
Here's the last one.
Yes.
Just also to help other mindsetters.
quick.
Offensive says, how do I master all the equations be given in the chapter of momentum?
Practice, practice, practice. The more you practice, the more you get used to what these questions look like. Download the past papers. This hasn't changed much from last year's curriculum and the year before. In fact, it hasn't changed much for the last 10 years. Get as many past questions as you possibly can. The more questions you do, the more you realize they're all the same. There's hundreds out there. Practice, practice, practice. That's the best way to do it.
All right.
And I think we've run out of time.
We've run out of time, but your last words also to encourage the mindsetters that are supplementing.
Yes, supplementing. Ask your teacher, okay? Hopefully they've got resources. If they don't, I know Mindset has excellent resources. We've still got stuff from last year. Get onto the education website. They have lots of past papers and go to your bookstores, get some study guides. Practice, practice, practice. It's with everything, okay? Also, get used to the equations and don't rely on your information sheet completely. Because remember, an equation like the total moment, that's not going to be on your information sheet. Okay? That's how you get used to it. Practice, practice, and practice. Okay.
And more it takes that.
Yes.
We do have supplementary school where we're giving you more lessons, extra lessons, even at night. So make sure that you get yourself some study notes. Also, get in groups. Ask some people. You'll never be ashamed. Don't be ashamed, actually. If you're struggling, ask. We have a website, which is learn.mindset.co.za. Visit that website and ask on Facebook, facebook.com/learnextra. Invite also your friends to join us on Facebook or follow us on Twitter @learnextra. It takes you to help other people for you to be helped also. So if you know something, probably someone doesn't know that thing. But from us today, we just want to say it's been a great day. Keep on believing in yourself, because when you stop believing in yourself, no one will ever believe in you. From us to you, peace.
explanation, okay? But let's...
Well, you can, just to show us how much you understand.
That would be
the
great.
concept,
I'd
yeah.
actually really like to hear some of those explanations, especially if you don't get it right. That sounds bad. But this is what I say to my learners all the time. You have to try in order for your teacher to help you. When I have a learner who says, I didn't do my homework because I didn't understand, I actually can't help them understand because I need to see what you've done wrong to see what's going on in your head.
Exactly. Try and fail rather than failing to try.
Absolutely. I like that. I like that. Okay. So let's go through some of the theory, just quick, and this should all be hopefully a bit of revision, okay? So the first thing is momentum is a vector. So we've got to remind ourselves what that means. With momentum being a vector, whoops, let me not put text. I want the pen. That's what I was looking for, okay? Vector means momentum has to have both direction and magnitude size, okay? So that's really important. So whenever you do a momentum question, and they just say calculate momentum, change momentum, anything like that, make sure you've got to put a direction in. Big problem if you don't. Number 2, it's defined, this is the definition, as the product of velocity and mass, which gives me P equals mv. Momentum's probably one of the few physical quantities that gets used almost. It's going to be posted on Facebook. I think it's on its way, but let's just read it together. When a large truck collides with a car, often the car will experience a greater amount of damage. This is because, and now you need to choose the correct answer. Number A, the car experiences a greater force than the truck. Okay, that's the first one. B, the truck experiences a smaller impulse. Okay. C, the car experiences a greater acceleration. Or D, the truck's change, say in momentum is smaller, not as momentum. Okay, that should be is. The truck's change in momentum is smaller. So I'm asking you, why do cars get more damage when they collide with a truck? Okay, is it because the car experiences a greater force? Because the truck experiences a smaller impulse? Because the car has a greater acceleration, or because the truck's change in momentum is smaller. Okay, so you need to have a think about it, and these answers have been very specifically set up because we'll see how you do it to show some misconceptions, and hopefully we'll help you out along the way. Okay, so have a think about it. Hopefully by the end of the show you'll have the right answer, and we'll have a lot of people with the right answer. That's what we want. Okay, and then they can just start putting their answers on. Hey,
exactly.
C A C B. Don't need to put an
Hello to you all, class of 2014 matriculants. This is your time. My name is AB Abram, and we're all up and ready to give you a most jam-packed educational show ever. This is Learn Extra Live, and we're here to bang it with Tracy.
Hi, Abram. How are you?
I'm fine, thanks, and you?
Good, thanks. I'm excited to get going and get started with our guinea pigs here because they got the new curriculum, so it's going to be
must be
interesting.
exciting, hey? Because
it's exciting and scary. But you know what? I think it's going to be a great year, and I'm excited for them, and they can do this.
But with the right skills and resources that we have as mindset, you can't go wrong.
Practice.
You can't.
No.
Exactly. What are we doing today?
Today we're going to do momentum and impulse. Hopefully most of them have done it already. I really am hoping that. I know my learners have actually just written their first test on it. So they don't like me very much right now, but it's okay. So I just have to quickly do this. Hello to my learners. Byron. Hello.
Can you hear them shouting?
Yeah,
hi.
I can hear it. And if he isn't watching, I'm going to smack him at school tomorrow. Just that, didn't say that. I will reprimand him quite severely.
All right.
Yes.
Minus some marks there.
No, but we just correctly in everyday language. Because we often talk about momentum, and we say in a rugby match, and we'll say that the momentum of the rugby player when he got tackled is what put him over the try line. Okay, and what commentators are referring to is the motion. Okay, and they're talking about how fast he was going, or how big he is, or something to that effect. So, and that's almost correct. So it's okay if we think of momentum in terms of motion. Objects have to be moving to get motion. Okay, so that's quite important. Now the equation is P equals mv, and remember it's a little p, not capital. Capital P stands for power, and they will mark you wrong. Okay, so P is momentum, m is mass, V is velocity. Remember, you have to do it in SI units, so mass is in kilograms, velocity in meters per second, and together those units give me the units of momentum. Because if I go, this is kilogram, meters per second. Kilogram meters per second, straight from the units of mass and velocity. Okay, so that's really nice. Must have a direction. Now, added to that, I don't think you're going to get a lot of questions with a single object bouncing off a wall, all of that sort of stuff, but we're going to deal with those just now. That brings us to the whole concept of impulse. Now, impulse is a strange, in momentum and impulse, it's a really nice section. It's actually a nice, easy section to get marks if you get the concept. So hopefully we can get those foundations.
Flow together, exactly. Well, to help you, here are some resources that we have for you. We have notes that you can download all for free. Visit our website, which is lan.mindset.co.za. Follow us on Twitter at LanExtra. Like our page and invite all your friends to like our page also on Facebook. Currently, we're sitting at about 65,000 and more likes on Facebook. So let's get everybody join in the Mindset tribe. But for today, we also have a challenge question.
We do, which I'm going to do in a second once I've introduced the lesson, but I've got a challenge question for them, so we're going to see how they do.
Well, we'll post it on Facebook and make sure that your answers are on that post. Yeah, let's do this.
Should we get going?
Yeah.
Okay, brilliant. Guys, please interact with us. We really want to answer your questions, okay? We want to see what you guys are doing. So just in terms of what are we doing today, we are going to discuss the important terms in momentum and impulse. It's really important. Hopefully you'll get the difference between some of them. And then we're going to discuss impulse, conservation of momentum, and conservation of kinetic energy, which is a really important part of this section. Okay? But straight away, let's just jump in there and give you the challenge question. And it's a very important question because it comes up a lot. Wrong way. There we go. So this is our challenge question. All right?